Good morning, everyone. Today we are going to continue our talk about phase transformation, the part three. And here are today's objectives. First, we want to learn continuous cooling transformation diagrams, and we want to learn mechanical behavior of iron-carbon alloys, and then we will learn tempered martensite. So this is a very, very important topic. And last time we have learned martensite, and we know that martensite itself is too brittle and also too hard to be used in industrial applications. So we need to do something before we use it. And this is called tempering. Um, First, we talk bainite. So bainite is another iron and cementite transformation product. This is we talk about this bainite. This is a bainite, elongated cementite particles in alpha ferrite matrix diffusion controlled. Isothermal transformation diagram. It means that the temperature we are going to lower to is kept constant. Isothermal transfer diagram. So here, this is a give example. The composition is 0.76 with percent of this carbon. And so here is this is uh, so this curve is called begin curve, and so this curve is called completion curve. And in the middle is called 50% curve. So this dotted curve. Uh, this uh, this dotted curve here. So here is a micrograph of this bainite. Actually, this is a matrix of alpha ferrite matrix, and we have elongated cementite particles. So as you can see, this is an elongated one. So here, at this temperature, if we lower the temperature from um, austenite here, please see my mouse here, and lower this one and to about 600, and then keep this 600 degrees C constant, and as the time goes, finally, and we will get 100% perlite. And however, for this temperature, if we lower the temperature to a lower one, is lower than 500, which is lower than the level of the nodes of these three curves. And then we keep this constant, keep the temperature constant. As the time goes, and we will get the bainite. That means bainite is the resultant phase at lower temperature, and perlite is the um, resultant phase at higher temperature. And so we also talk about, actually, we talked about this one already in our previous class. This is kind of um, refresh your memory. Spheroidite, another microstructure for the iron and iron carbon system. So as the name suggests, spheroidite like a sphere. So this is cemented particles within our alpha ferrite matrix. And formation requires diffusion formation. And heat bainite or perlite at a temperature just below the eutectoid and for a long time. And I also told you the driving force is that the reduction of the alpha ferrite and cementite interfacial area. And because we know and the sphere is the shape that gives us the lowest surface energy. I also told you guys for all the systems in the universe, it has tendency to to minimize the potential energy of this system. And why? Because a system with lower potential energy is more stable. And then we talk about martensite here, a non-equilibrium transformation product, martensite. And so martensite, this is from austenite gamma, which is has FCC crystal structure, to martensite BCT. This is the BCT here. So here is in this micrograph. So this dark needle-like this stuff, um, they are the martensite, and other stuff, lighter stuff, is austenite. And you can see also clearly after we finish this phase transformation, and not all of this austenite has been transformed into martensite. Only part of austenite has transformed into uh, martensite. So here is the Fe atom, the size here, iron. This is a potential C atom size in the middle. So here as a thermal transformation diagram. And so here is we use the same diagram, but now if we use a higher cooling rate, and the higher because the higher cooling rate, so this is the cooling rate curve, we will not intersect these three curves, especially this nose. And as a result, with this so high cooling rate, and we will not have the either pearlite or this bainite. Instead, we will get this martensite here. And gamma austenite to martensite transformation, and it is rapid because the carbon atoms or iron atoms, they do not have enough time to diffuse. So we can see this diffusion rates. The percentage of transformation depends only on the final temperature to which rapidly cooled. Any questions regarding this slide? No question? We talk about this formation, martensite formation. So this is the FCC slow cooling, and we will have alpha BCC plus this cementite. All right, so this is whether it is a bainite or pearlite depends on the final temperature, and you lower the austenite too. So if the cooling rate is high, and we call this quenching, and you should write down this is called quenching. For quenching, we will get this martensite. Martensite is a single phase. It has body centered tetragonal BCT crystal structure, tetragonal BCT structure, and diffusion-less transformation BCT. If this is a carbon composition is greater than 0.15 with percent C. BCT has few slip planes and hard and brittle because it has few slip planes. So um, if there is the tendency for plastic deformation, the system just tell that we don't have, I cannot accommodate this plastic deformation. Then this is the brittle. This is the crack instead of plastic deformation. So this is from martensite. If we lower, as I said, martensite itself is very hard and brittle. It cannot be used in engineering applications, industrial applications. Instead, if we want to use the beautiful characteristic of martensite, means being hard and strong, and you need to temper it. And that means tempering means that we elevate the temperature to a certain temperature, then we hold it for a certain amount of time, and then we will get tempered martensite. This tempered martensite is not as hard as the martensite before tempering, but um, it is still very strong, but the ductility is improved also. As a result, tempered martensite can be used directly for various engineering applications. So this phase transformation of alloys I showed you is um, if we add some alloying elements here, for example, chromium, nickel, molybdenum, silicon, and manganese. And so this, if we alloying these kind of elements in our um, material, and this is elements can retard the transformation of gamma austenite to this ferrite and this cementite. And so that means, and So this is nodes. The nodes of these is three curves will be moved to the right, and that means even with lower the cooling rate, and you might get this martensite. Does that make sense? Okay. You can see effect of adding other elements change transition temperature. Then we talk about the continuous cooling, the transformation diagram. The conversion of isothermal, previously we talked about isothermal. Isothermal means that and we hold the desired final temperature constant. But we talk now from isothermal transformation diagram to continuous cooling transformation diagram. So you can look at here. Okay, so this is a austenite to bainite to perlite. So here, this is a cooling rate, is a cooling curve, and this cooling curve, and it will intersect, and so this is at this point, right? This is continuously cooling from this temperature to the room temperature, and it goes down. Well, this is the austenite, and so this is austenite. So here, and so here is the slow cooling curve and full annealing. So this is moderately rapid cooling curve and this normalizing. So here we will get fine perlite, and here we will get this is the coarse perlite. And so here is a begin curve, and this is a final curve. You continuously going down. And continuous cooling down transformation diagrams here. So if here, okay, so you can see if we this cooling curve and goes this way, this goes this way, and this cooling curve goes this way. And so here is this diagram. You can see this is uh, more. This is the beautiful one. Here is the continuous cooling transformation diagram for alloy and steel, and this is type 4340 and several superimposed cooling curves. One cooling curve of the final microstructure of this alloy and the transformation that occur during cooling. So here, this is a critical cooling rate, and this critical cooling rate means that if your cooling rate is higher than this one, and you will get martensite. So this is a bainite nodes, and so this is the austenite to ferrite, and all this is cooling rate is given here. From here is austenite to bainite. Here is austenite to martensite. And you should know this one very well. And then we talk about mechanical properties and influence of carbon uh, content. So first one we talk about perlite, right? The perlite, and so this is ferrite is softened, ferrite is soft, perlite is medium. So this is carbon concentration composition is less than 76 with percentage. So here is a carbon composition is greater than 76.76 with percentage. So this is a perlite, and so this is a cementite. Cementite is hard. So here is the tensile strength, and so this is a tensile. Uh, this is the yield strength. So hypo and hyper, we know that, right? Hypo is the carbon composition is lower than this eutectoid uh, temperature. Eutectoid composition. Hyper is the composition that is higher than this eutectoid this composition. So we can have different um, combination will give have different yield strengths, and so this is tensile strength. Um, for the elongation actually is ductility, and so this is a hypo and this is a hyper, and we can see as the carbon composition increases, the elongation percentage decreases substantially, and so you should know this and how the composition, carbon composition affects this is the material's mechanical property. So increased C content, we can get uh, this is yield strength, and this is ultimate strength. Ultimate strength, and some people use TS, some people use the UTS. This is a fine pearlite versus coarse pearlite versus the spheroidite, and so you can see the also the hypo and hyper. This is a bainite. This is a Brinell hardness. Brinell hardness, so this is ductility. For hardness, fine pearlite is greater than coarse pearlite, is greater than spheroidite. The percentage of the area we know fine pearlite is lowest, coarse is medium, and spheroidite is highest. As I said, hardness is proportional to the strength, and strength is competing mechanical property with the ductility, which means that if a material has higher strength, usually this guy has lower ductility. So here you can see the Brinell hardness for different fine, fine pearlite, coarse pearlite, and spheroidite for all different um, carbon composition, and this is increases as this is carbon composition increases. And however, as the carbon composition increases, the ductility for all these three microstructures, they are decreasing substantially, especially for this fine pearlite. My bottom line is that you know how to interpret these figures if I present some figures for you in the quiz or uh, in the exam. Femplate versus martensite, and we know martensite is the most um, the hardest material, right? So hardest material. This is Brinell and hardness. And hardness, we have several different hardness designations. One is HRC, Rockwell. One is Brinell. One is Knoop. One is uh, Knoop. One is this is another one. So this is Brinell and uh, Rockwell, and they are commonly used one. Hardness, you can see fine pearlite is far below than the martensite. The tempered martensite carried out at temperature between 250 and the 650 degrees C. And this heat treat martensite to form tempered martensite. And tempered martensite less brittle than martensite. And tempering reduces internal stress caused by quenching. Quenching means very, very high cooling rate. And so this is a temperature, different temperature for tempering temperature. And we have different the ultimate strength along with the yield strength. Also, um, the ductility also are different. And for this is ultimate strength and yield strength as the temperature increases, and these two guys are decreasing. And however, for ductility, uh, it increases if you elevate the temperature for tempering. And so this one and shows uh, so the tempering produces extremely small cemented particles surrounded by this is the particles surrounded by this austenite. And tempering decreases ultimate strength, yield strength, but increases this elongation, ductility. And here is the equation about tempered martensite. Martensite, BCT, body-centered tetragonal single phase. If we elevated temperature, we will get this alpha plus this is a cemented phase. And cemented is uh, hard, or this alpha ferrite is ductile. And this is a summary of possible transformations for this iron and iron carbide, iron and this is cementite, the phase diagram. This austenite and slow cool, and we have pearlite. This pearlite we will have alpha and plus this is cemented layers and a pearl-eutectoid phase. Moderate cool we have bainite. Bainite in bainite we have alpha plus elongated cemented particles. If very rapid cooling, and we call quenching, and we will have martensite, which is a polycentered tetragonal phase diffusion-less transformation. And so as I said, this one cannot be used directly. And then we usually reheat it to a certain temperature and hold it for a while. And then we will get a tempered martensite, which is composed of the ductile ferrite and very fine these cementite particles. Cementite particles is very hard. As a result, after tempering, this tempered martensite can be used for the industry. Here is the trend. Martensite, tempered martensite, bainite, fine pearlite, coarse pearlite, spheroidite. The strength going up. Right? Is the strength going up. However, ductility going down. As I said, so this is a strength and ductility, and they are two competing mechanical properties. If one is high, another one must be low. And no material can possess both high strength and high ductility. Why? Because the stress and ductility, they are defined, their definition is opposite. Any questions so far? Uh, Without any question, and I will ask you guys to review these lecture notes and before you go to bed tonight. And as I always say, review the lecture notes, review the notes you have taken uh, for during the daytime, and then you can just maximize the knowledge retention. And so has been confirmed by research. And with other, I hope you have a wonderful day.